Welcome to the session. In this particular session, we will be understanding the numerical integration method. So one of our assignment will be based on those methods. In this session, we will be understanding about the introduction of numerical integration. We will be covering two types of methods such as Newton-Cotes method and Gauss-Legendre Integration method, or sometimes we call it as a Gauss quadrature rule. Now in this case, Newton-Cotes method, there are certain methods which we will be understanding and making the code. And at the last, there are some important instructions for making the codes for the assignment, for this assignment. Let us begin with the introduction now. First of all, let us understand what are the needs of numerical integration, because as you know that we can even find integration by our hand. But sometimes when function do not possess closed form solution, then in that case, we will be using the numerical integration. Second is the closed form solutions exist, but these solutions are complex and difficult to use for calculations. So in those cases, we are going to use numerical integration. Third case could be data for variables are available in the form of table, but no mathematical relationship between them is known. So as is often the case with the experimental data. So in that case, when the experimental data is there and we want to make an integration, then we are going to use numerical integration in those cases. So what we understand by numerical integration or by integration, look at the figure on the right hand side. Suppose we want to integrate a function as it is given from x0 to x1. So the integration says that the area under the curve from x0 to x1 will become the integrand of this function. So in order to find that, as you can see, I can find using graphical method, I can make the grids and I can count the number of grids that will become the area under the curve. But what we will find that these kind of approaches are cumbersome and time consuming approach. So here we are looking for those numerical integration method that use simple arithmetic operation to compute the area under the curve. So as you can see, the basic method involves, suppose if it is a one single integral function, so fx is just made of one variable. So in that case, the equivalent numerical integration we can write as a summation over I equals to 0 to ni wi fi. So sometimes it is also called as omega I f of xi. What it means that, so omega I is some kind of a weights and xi is some intermediate points where we are trying to find out the objective function. So in similar case, if we have a double integral, then we will be using two summation. We will be having two omegas as omega I, omega j, and then we will be calculating the function value at xi, yj. And for the third integral as well, we are going to have three summations, omega I, omega j, omega k, and the function value of xi, yj, and zk. What you will see here is that the xi, yj, and zk, all of them are the sampling points. And using those sampling points and the weights which are represented as omega ijk, that will be used for finding the numerical integration. So with this introduction, let us move to Newton-Cotes method. Now Newton-Cotes formula is the most popular and widely used numerical integration formula. It forms the basis for a number of numerical integration methods known as Newton-Cotes methods. The derivation of Newton-Cotes formula is based on polynomial interpolation. So suppose we have nth degree polynomial that interpolates the value of the function say fx at n plus 1 equally spaced point that can be used to replace the integrand fx of the integral. So as we know, this integral which you can see from x0 to x1 fx dx will be substituted by the nth degree polynomial, and we are going to calculate the value at n plus 1 evenly spaced point. So the resulting formula generally referred to as n plus 1 point Newton-Cotes formula. Now here, what we are going to do is since we know the lower and upper limit for the integration x0 to x1, we are going to divide this particular range into the number of steps or interpolation points, such as xi, and I we are taking from 0 to n. These formulas is then the formula is referred to as a closed form, else open form. Now here in this particular assignment, we will be considering the closed form methods. Let us begin with the first method called trapezoidal rule. This method we have already learned earlier, and in this method it is the first and the simplest form of the Newton-Cotes method. It uses 2 points. So since it is using 2 points, it can interpolate first order degree of a polynomial. Now let us look at the figure on the right hand side. We have say x0 to x1. Now since if suppose these two values x0 to x1, if they are close to each other, then what we can do is we can use the trapezoidal rule as I equals to it, and that will be equals to summation of x divided by 2 f of x0 plus f of x1. Now the function value of x0 and x1 we can find it out. And what is delta x? Delta x is x1 minus x0 divided by 2. Another one is called composite trapezoidal rule. In this particular case, we are going to divide this range x0 to x1 into the number of small intervals. So let us see that. So suppose we have x0 and then we have x1. We are going to divide in say n number of intervals. So in this case, we are going to take the summation of each area, as you can see in the figure on the right hand side. So what is the formula? As you can see on equation, as you can see the equation number 4, we have the value as delta x by 2, and we know delta x is x0 minus x1 minus x0 divided by 2. Sorry, this delta x is x0 x1 minus the delta x here is x1 minus x0 divided by n. N will be the number of intervals or steps we want. In the bigger bracket inside, you can see the function value at x0 plus function value at x1 plus 2 times of the summation of f of xi. And this summation is from I equal to 1 to n minus 1. Now the point is how I can calculate xi. So xi we can write as xi is equals to x0. So the first point is starting point plus I times of a delta x. So the delta x we already calculated as x1 minus x0 divided by n. So that way we are going to find it, and we can find the integral value, numerical integral value for this particular function. Now let us understand the algorithmic representation here. So I'm describing you for the composite trapezoidal rule, and rest of the rules you can make it with the help of such kind of an algorithm. So I will be discussing only this algorithm here. First of all, we have to define a function. Once we have defined the function, we have to set what is our lower and upper limit of the integration, that is x0 and x1. Similarly, how many subsets or interval we want, say n. Then we are going to calculate the delta x value, which is x1 minus x0 divided by n. Then let us calculate the integral value as I equals to f x0 plus function value at x1. Now this we are calculating because that will remain the same during our calculation. Now come to the step number 5. Here we are running a loop for I, which is starting from 1 till I is smaller than n minus 1, meaning that I will be running till n minus 1 only, and then I plus plus. So in this particular for loop, first let us calculate xi value. So xi is equals to x0 plus I delta x. So in this case, once we have calculated xi value, in step 7, we calculate I as I plus 2 times of f of xi. This is exactly the same formula we understood it. Now what is the advantage of I equal to I plus 2f of xi? That whatever be the previous value of xi, we are adding this new value as 2 of the function value at xi. Once this loop is over in step 9, we will update I as delta x by 2 into I. And we will print the value of I, and that is become the integration of the function fx. Now here it is important to note that if suppose we are given 2 or 3 functions, so in that case we don't have to write different code for those functions. What we can do here is only at step 1 we will change the function from function 1 says to function 2, and rest of the algorithm will become the same. Now coming to the midpoint rule. So as the name suggests, the midpoint rule says that we are going to find a midpoint which is half of x0 plus x1. And looking at this figure, you can see that we have x0 and x1, and we are going to find the middle point. In this case, the integration will become delta x times of function value at x mid. So only one function value is we have to need it. So in this case, if you correlate with our algorithmic representation, then we don't need any for loop. We'll just in one step, we'll calculate delta x value, then multiply this value at the function value at the midpoint. Now, if we want to find the composite midpoint, composite sense that we are going to divide x0 to x1 in n number of intervals. So looking at the figure on the right hand side, we are going to divide this interval into n, small n steps. So the integral as of now it will become is delta x times of summation of I equals to 0 to n minus 1, then the function value of xi. And what is xi here? Xi is equals to x0, which is the lower limit, plus inside the bracket, we have I plus 1 by 2, and then everything multiplied by delta x. Now what is delta x here? Similar to the trapezoidal rule, it is x1 minus x0 divided by n. Now, as you know, in this equation number 6, if I have to fit this into our algorithmic representation, then I have to write this particular thing into the for loop, because every summation will be converted into the for loop. Now coming to the Simpson's 1/3 rule, the function is approximated by a second order polynomial which passes through 3 sampling point. So as you can see, we need 3 sampling point. Now since we are going to find an integration from x0 to x1, so x0 is first point, x1 is second point, and what is the third point, which is x0 plus x1 divided by 2. What this method says that the integral value will become delta x divided by 3, and inside the bracket we have function value at x0 plus 4 times the function value of x mid. X mid means x0 plus x1 divided by 2 plus the function value at x3. Well, in this particular case, you can see that we don't need any for loop. We can directly use the formula here, and we can find the value of integral. Here the delta x value previous to our case x1 minus x0 divided by 2. It is important to note that Simpson's 1/3 rule is exact up to degree 3, although it is based on the quadratic equation. Now the same Simpson rule can be converted for the composite Simpson rule, in which we will be dividing the range of x0 to x1 into n number of equal segments. So as of now, all the methods we are dividing x0 to x1 in equal number of segments. So in this case, the step size is 1 divided by n x1 minus x0, similar to the trapezoidal rule. And here xi equals to xi plus x0 plus I times of delta x. This is also similar to the Simpson trapezoidal rule. And then we have a value of integral. This is the value of integral, which is equals to delta x divided by 3. Now delta x already given there, and inside this particular big bracket, we have function value of x0, then 4 times of the summation of f of x 2i minus 1. So 2i minus 1 is in the subscript, and the rule and the summation is from I equal to 1 to n by 2. Similarly, we have 2 times of summation I equal to 1 to n by 2 minus 1, and the function value at x 2i plus f of xi. Now here it is important to note that these 2 summation will become for loop. So if we are going to use the same algorithm representation, then of the trapezoidal rule, then we are going to use 2 for loop here. Now let us come to the Simpson's 3 by 8 rule that considers 4 sampling points so that the rule can be extract for fx of degree 3. So what is the formula here? 3 delta x divided by 8. In this case, this is f of x0 plus 3 times of xm plus 3 times of xn plus f of x1. Now here, looking at the formula, you can see that we don't need any for loop here. Directly calculating the formula, adding up, multiplying by 3 times of delta x divided by 8, we will going to get a Simpson's 3-8 rule. Now here delta x is 1 by 3. Please note that the delta x is changed now 1 divided by 3 x1 minus x0. And this equation is called 3 by 8 rule. Here the xm value is x0 plus delta x and xn value is x0 plus 2 times of delta x. Now come to the Boole's rule here. Now this particular method uses 5 sampling point. As you can see, we have the formula as d 3 times of delta x divided by 45, and inside the bracket we have 7 times of f of x0 plus 32 times of xm plus 12 times of the function value at xn plus 32 times of function value of x0. So please note that it is x0, not x0, plus 7 times of the function value at x1. In this case, the delta x is 1 by 4 x1 minus x0. So this is important to note that. And xm is x0 plus delta x. Xn is equals to x0 plus 2 times of delta x. And x0 is equals to x0 plus 3 times of delta x. In this particular equation number 10, when we are going to implement it, we don't need any for loop. Calculating the function value at 5 points, some summation of that, and that summation is then finally multiplied by 3 times of delta x divided by 45. Now we are coming to the Gauss-Legendre Integration Method or Gauss-Quadrature Method. Now this Gauss-Legendre method, or popularly known as Gauss Integration Method or a Gauss-Quadrature rule, is based on the concept that the accuracy of numerical integration can be improved by choosing the sampling point wisely rather than on the basis of equal spacing. Now, as we have understood from the previous methods, where that comes under Newton-Cotes methods, that when we are dividing from x0 to x1, we are dividing into equal spaces. But in this case, we will be using some sampling points and the weights that will help us to find the integration. In this method, the sampling point lies inside the domain of integration and the endpoints are not used in computation. So here, the integration what we had earlier, we are going to convert x0 to -1, x1 to +1, and x to zeta. So this particular integral from -1 to +1 f zeta d zeta is equals to the summation over I equal to 1 to n zeta wi or omega I and the function value of zeta I. Now what you can see that in this particular case, our integral should lie from -1 to +1. So the earlier integral, which was x0 to x1, that need to be transformed in such a way our limit should change from x0 from -1 to +1. Here zeta I are the sampling points, which are known as Gauss points, and omega i's are the Gauss weights. Now the problem, now as we know what should be the points and the weights in this case. And so the problem is to compute the location of the sampling points and to choose the appropriate weight. So Gauss integration method assumes that x0 is -1 and x1 is +1. In doing so, Gauss point location and weight can be readily available. So in this case, I have given you a website at the bottom, the number 1. You can see that those points can be used and that are given for n is equals to 64 point. In case we want more, this MATLAB script is also available online. So the number 2 link, you can go through it. You can download the MATLAB code and it will generate the number of Gauss points, large number of Gauss points for you. So how this table look like? For n equals to 1, 2, 3, we are going to have I, j or a k, so 1, 1, 2 or 1, 3. And we are going to have the different kinds of a weight and the different Gauss points as well. Here, important to note that considering polynomial integrand, it has been proved that the use of n Gauss points give the exact result of polynomial integrand of up to the order of 2n minus 1. Meaning that if suppose we have a linear function putting into 2n minus 1 equal to 1, this means n equals to 1. It says that for a linear integrand p equal to 1 Gauss point will be sufficient to give the exact result of integration, which is a very good property here. If suppose we have an order of a 3, then we need 3 Gauss points to find the integral here. Now in this Gauss quadrature rule, suppose we have this integration, double integral. So in this double integral, as you can see, the limit from -1 to +1 and the function, this is equivalent to the 2 summation over number of zeta, number of eta, weights, and the function values. Similarly, the triple integral can be converted into the 3 summations. So as we remember that these, when we are going to make a code for here, these summations will be converted into the for loop. So the upper for loop will be from I equal to 1 to n zeta. Inside that for loop, there is another for loop for j equal to 1 to n eta. So these are the nested for loop will be there. You just take care of that. Now, and the second important point which you have to consider is you have to save all the Gauss points in your code. So in that case, suppose you want to use just 1 point or you want to use set of 3 points or more, then you can directly take the values which are saved. So you have to save those values in an array and so that you can extract the Gauss points as well as Gauss weights. There are important instructions for this assignment. Please write a separate function in C for each integration rule. So we have gone through many rule now. Also make a dedicated function for a polynomial evaluation at the sampling point. This will help you in using the same program for different polynomials by just rewriting the function only without the need to change the whole code. So as you know, the formula will not change. So therefore, if you remember the algorithmic representation, then in that case, what you need to do is only function has to be changed. Rest of the rules will remain the same. So as and when you will get different questions, you have to just change the objective function value, or you have to just change the function value. That's it. Second is during the evaluation of this assignment, for each problem, please report the error with respect to the exact answer wherever applicable. So it is preferred that you have to make a table and you will show all your result, what you are getting from the code as well as the exact result. Also, it will be desirable that you also carry out a parametric study, like increasing the number of intervals or increasing the number of Gauss integration points, and report your observation, because you want to see that if you increase the number of, say, intervals, how your solution will be improving and what is the error at that time. There are more instructions here. You have to read the handout and solve the questions. So the assignment questions are given at the end of the handouts. The concepts are described there, and also the guidelines for assignment are also given in the handout. Please note that the Viva question will be asked from the handout as well as from the code which you have made and submitting to us. I'm sharing you 2 websites where you can find the algorithmic code as well as C or C++ code. Only you can refer them, but please make sure that I have written in the last line. Make sure that you write your own code. Copying the assignment will reward 0 marks. So therefore, you can take the help, you can understand the structure, but the code should be yours. So with this, I'm concluding this particular session. Now you are ready to solve the assignment on numerical integration. Thank you very much.